Hi, I'm Aaron Christianson. Welcome to my talk for JuliaCon 2020 about dispatching design patterns. Um, I live in Germany, in Frankfurt. I am a programmer at the Goethe University. So my talk today is about design patterns. The talk has a GitHub repo at my GitHub account, Ninja Aaron / dispatching design patterns. Where there's transcripts and code samples and links and stuff like that. So if you want to check out anything in this talk in more detail, is more there. All right, so a design pattern is a formal way of documenting a general reusable solution to a design problem in a particular field or field of expertise, um, especially in this case, software design. Dispatch, this is not the first definition of dispatch or the second definition. Went down to the seventh and eighth definitions. To destroy quickly and efficiently. To pass on for further processing is the next definition, especially via dispatch table. So Julia, in some ways, destroys a lot of traditional design patterns because it is different than what a lot of programmers are used to. Julia looks like Python or Ruby, looks like MATLAB, some other languages, but the objects are actually very different. Julia doesn't have classes. Julia interfaces instead are designed in terms of structs, just um, simple composite data type. Multiple dispatch, you also have some abstract types in there and stuff. And it's more similar to the object orientation in Common Lisp, which is, I guess, a language far fewer programmers are familiar with. For object-oriented programmers, Julia's objects may be disorienting. So that's what I mean by in the first sense I had of dispatching design patterns. It kind of wrecks what you expected. Now, I answer a lot of questions on Quora about Julia. One of the things people are asking about frequently is, how can you have a large, complex project in Julia if you can't even have classes, right? How can you make appropriate abstractions that scale up? So in some cases, some of the popular design patterns aren't really necessary in Julia, like some of them in Gang of Four, if you're familiar with those. For example, the strategy pattern can just be replaced by passing a function to another function, right? You can do this in any functional language and in most dynamically typed languages. Instead of having a whole bunch of classes to think about your strategies, you can just have a function that you pass in. You go to a party, you come up with your small talk strategy. Maybe you talk about the weather, you talk about your job, have some recent topic. So you find a human to talk to at the party. You use your small talk strategy. Hopefully there's no error, but if there is, you weep deeply and return home. If you want more examples of how some of the classic design patterns are kind of superseded in dynamic languages, Peter Norvig has a talk from 1996 called Design Patterns in Dynamic Languages, which goes over sort of stuff like this, how these design patterns are really replaced by language features in higher level languages. And he also has some more design patterns that emerge in dynamically typed languages. So let's get to encapsulation in Julia. So in Julia, you have structs. A struct is just a name for the type and data fields. Now the data fields each have a name and they have a type. You don't technically have to have a type in Julia, but types on structs is probably the most important thing you can do for the most important simple thing you can do for optimization in Julia. if you don't have the types there, you're going to have really bad performance. On the other hand, you don't really need types on functions as much in Julia, but it's very important to have them for structs. You also get a default constructor, right? So you put in a value for each parameter, and it constructs your struct. Attribute access looks like other languages. You got your period. Oh, by the way, all attributes or fields or whatever in Julia are public, right? So any function, any user, anyone can access this data. I wish there was a little bit more way to control privacy of data in Julia, but there is not. So structs in Julia are immutable by default. This is usually good. So we try to change one of the fields in our point, and it doesn't work, right? A point is a point. It shouldn't change. If you have another point, then it's another point. It's also good for performance, immutability. The compiler can see that and do some interesting optimizations. However, some objects do need to change over time. For example, if you have a starship, here we have the Enterprise, right? Our starship has a name and a location, which is the point that we defined previously. And we could change the location of the ship by giving it a new point, right? You can also have alternate constructors for structs. Simply take the constructor name and define another dispatch. This constructor helps us avoid having to write the point constructor every time we define a new ship. You can also have an internal constructor with new. So after your fields, you put in the constructor name again, and then you have how you wanted to use the default constructor, but you use new here because this name isn't available yet because it hasn't been defined yet, right? It's like the chicken and egg thing. So you have this new thing. And once you have an internal constructor, the default constructor goes away. It's no longer available. This can be good for doing sanity checks on variable values or something like this as well. Next, we have methods in Julia. So abstraction in general is about simplifying internal complexity. Our starship has a name and it has a point which has x and y coordinates. The user of the ship shouldn't necessarily have to care about all of that if it wants to move the ship. So our moving interface, we just want to have the heading in degrees and the distance. So we use that to calculate the change in y, the change in x, and then we update the location of the ship. Because the user shouldn't have to care about the trigonometry in order to make the ship move, right? Now, in object-oriented programming, methods specifically are about providing simple interfaces to composite data types. In Julia, methods are not attached to objects at all. They're attached to functions, but they're still defined in terms of types. So you can provide still these simple interfaces to complex data like you would in object-oriented programming. You just basically switch the order around, right? So instead of the object dot method, you have method and then the whatever objects. And it can be, I mean, the reason it's called multiple dispatch in Julia is because it actually dispatches on all of the different types. So it's a more complex method resolution situation. So here we have a rectangle with a width and a height and a square with just a length because that's the width and the height. But we define the same interface, the width and height interface for both of them. It just works a little bit differently internally. So when you call width or height on a rectangle, it's going to find the function definition it needs for that. And when you call it with a square, it's going to find the method definition it needs for the square. And it'll be able to correctly compute the area. So you can do basically everything you can do with methods in object-oriented languages, but you can do a lot more also. Now, if you want to have hierarchies of types with shared behavior, that's what Julia's abstract types are for. This is like if you would have a superclass in a classical object-oriented language, but an abstract type has no data layout. It just has the name, and then you can define methods in terms of the abstract type. So if you wanted to add together two areas, you don't care what the shapes are. You just use their area function, so it has to implement an area. Whatever a shape is has to implement area. You can also inherit from abstract types using the subtype operator. So we have struct circle is a subtype of shape. We have the diameter and the way to calculate the radius, and then we implement our area function for the circle. Abstract types can also be subtypes of other abstract types. So we have our abstract rectangle is a subtype of shape. And the way you calculate that, the area of a rectangle is width and height, right? And then we have our previous two shapes, the rectangle and the square, only this time they're in this hierarchy. They're a subtype of abstract rectangle, which is a subtype of shape, right? So they can use all the functions for all of that. So we can now combine areas for circles, squares, rectangles, right? And Julia will find the right dispatches for each of these. And it will optimize all of it at runtime with the just-in-time compiler. In some cases, there would be a runtime method lookup, but in this case, it can do it all efficiently. I'm going to skip about modules for now because this talk is longer than it should be. So we're going to go straight to parametric types. Yeah, statically typed dynamic typing. Now, it's not really dynamically typed. What you have with parametric types are type variables, which allow you to not define the type right away, but still allow you to kind of reason about them in a formal way, so to speak. Right? So now we have a point, and we don't want the point to necessarily have to be only float 64, right? So we have the point type constructor, which is a point, and then it takes a parameter to complete the type, which is a type variable. This t is a type variable. So x is going to have to be of type t, whatever that is when it happens, and y will be also of type t. So we send a couple of integers to the point constructor, and it constructs a point of int64 with the values 1 and 3. And t here is inferred to be int64. You can also use the type parameter explicitly. Sometimes it's helpful. Normally you don't need to in Julia. Normally it's all inferred. Now note that in this case, because there's only one type variable, it's the same value in every case, right? You can't have it be int64 and float, right? Because there's no room for that in the way we define this type. But we can have a constructor with multiple type variables, so we can have a type for each. And then you have a type of int64 and float64 if you want that. Now, one of the problems with just using t is that it could be any type, right? We can have a point of strings, which is nonsense, right? X and Y can't be strings, at least not normally. It's going to break a lot of assumptions about what a point is for our users, if somehow that's allowed to happen. So it would be nice if we could ensure that they were numeric types, just not so tight on the one float 64 type, although in practice it would probably be fine. Here I wrote sort of the obvious way to do it is to use the abstract type real, which encompasses most of the numeric types. So here I have two uint8, two unsigned 8-bit integers, literals that I'm passing in to make my real point. The problem is that because there's no type variable here, it's got the whole range of numeric types that it could be, so the compiler can't really optimize on that as early as it can if it has a concrete type to work with. So what we do here is use a type variable but constrain the type variable on the abstract type. Right? So then we still get the performance of using a concrete type at runtime. You can see it works with our integers. So we have our point of int, we have our point of float. But if we try to use point of string, because it's not a subtype of real, right? Point t is a subtype of real. It's not gonna dispatch. You're gonna get a method error. All right. Parameterized types are great for defining your own container types. This talk is a little bit longer than it should be, so I'm gonna go through this part quick. This is a linked list. You can see more on the GitHub repo. So it's got its value in the head and then the rest of the list in the tail, or nil, which is to show that it's the end of the list. Here's a function to turn an abstract array into a list. In this case, we use this where thing. This is kind of interesting. This lets you get a type parameter in the context of a function or in another context, which we use here in case the abstract array would have its element type would be abstract. Then we would also want the list to be abstract. Yeah. We implement the iteration protocol. I'm not going to go into how that works, but implementing protocols is something you do frequently in Julia. You override some function in base and it gives you control over syntax. In this case, it gives you for loops, right? So now we can make our linked list and we can iterate over it. And it can be of int or it can be of string because we have this type variable, but it'll still be efficient because the types can be inferred with this type variable. All right. So now we get to the trait pattern. This is a more advanced topic in Julia. One thing that Julia lacks that some languages have is a way to define an interface and then implement interfaces on subtypes, but without having it be part of a hierarchy. So right, we can have two unrelated interfaces like num, that's for numeric interface for numeric operations, and ord, which is for ordering, for sorting, things like that. Rust has features like this. Haskell has features like this. Swift, a lot of languages have this feature. In Julia, having this be part of the type system would be difficult because the way method resolution works is it looks for the most specific dispatch. And then it takes that. And if it's not in a strict hierarchy, it's difficult to say what most specific actually means. So this, I don't think, is likely to become traits or type classes or whatever are probably not going to be in a future version of Julia for that reason. On the other hand, it maybe isn't the hugest problem because you can implement any interface on any type in Julia without without having the type be part of a hierarchy, right? All right, here's an example of a trait from base. So we take our linked list that we can iterate over from the previous example, and we try to use map on it, right? So we try to apply a function to each item in the list. And it doesn't work because the list doesn't have a length method. Now you'd think you could do it with anything that implements iteration. We take an object like a file. So here we create a file with 3 lines foobar baz, and we get the lines. Each line gets each line iteratively, asynchronously. So the runtime doesn't know how long the file is going to be when it's dealing with an each line object. There's no length method for it, but nonetheless, the map function still works, right? We can still get our foobar baz. How is that? How come the list we have needs a length, but each line doesn't need a length? So what you have to do here is add an iterator size trait to the type. In this case, you do base iterator size and then put your type in there, and the trait we give it is size unknown. So then it's not going to look for a length function. All right. So what's going on here? If you go into generator.jl in the code for base, you're going to see this abstract type iterator size, and then you have all these different ways of thinking about iterator size, right? Size unknown, has length, has shape, is infinite. And this can give, they don't do anything, they have no data layout, but they can give extra information to the compiler that it can use for dispatches. So a little further down in the file, we see this iterator size equals type of x, right? And then for any type, it's not specific about which type here, it's just has length. So it assumes that any user created type is going to have a length method, which I think is a bad assumption, but it's probably too late to change it. When you can override that when you implement the size unknown, like we did on the linked list. You can also create your own traits. This is a simple one with no subtypes, although with subtypes is probably the most useful case. This one we can use it as more like a contract to make sure type implements a certain interface. Here we throw an error if the type doesn't implement the trait when we try to add foo and bar. So foo and bar need to have a function foo of x and bar of x in order to work. So the way this works is you define it on x, and the definition of x is you try to get the trait foo bar for x. And then it looks for that type in the real dispatch, and then it performs the thing. Unfortunately, as defined, it doesn't ensure that it has the required interface because we didn't implement foo or bar on int, and it still worked. So you can use this like a function to register it that will check if it has the required interface first, and then eval foo bar. Of course, as mentioned, it's more useful for this previous case of having different approaches to the same task that will look for a trait of a subtype and it'll know how to approach a certain task, like with iterator size. But contracts are also interesting, I think. Right. So yeah, here's an example where we implement foo and bar on int, and then we can register it, and then we can add foo bar, right? So dispatches for pattern matching. If you've used also Haskell or Rust or OCaml or Scala or Kotlin or whatever, you might have encountered algebraic data types and pattern matching. Julia does not have pattern matching. Oh, here's an example of pattern matching in Haskell. So you can define a factorial function in terms of the terminal case, which is 0. Factorial 0 is 1. And then you define the other cases in terms of in a recursive term, right? So it'll keep taking x until x is 0 and use that to compute the factorial. Julia doesn't have it, but if you know one of these languages, one of the main cases you have is you'll have sort of tags, and each tag belongs with a different type. It's like a tagged union or something that you could do in C or any other language. And you can match on those tags and those values and use that to choose the correct dispatch for your function. Julia's type dispatch isn't exactly the same, but you can do something similar because you do have this ability to sort of match different types with different function dispatches, right? So we're going to define a really stupid macro that will replace every instance of the number 1 with x. So the first is if it gets an atom, that's like the lowest possible thing in the abstract syntax tree, then it will return the symbol x, otherwise it'll just return the atom unchanged. And then for an expression which has a lot of symbols and possibly other expressions in it, other kinds of atoms, it will just call the replace function on each node recursively. So it's the same kind of pattern, right? In this case, we define x as 10, and then we have 5 plus 1, but the 1 gets replaced with x, which gets replaced with 10, right? As you can see, this is completely idiotic and useless. However, you can probably think of something much more interesting to do with it. This can also be useful for other recursively defined types, like our linked list that we had previously. So we define again the terminal case, and then we define what to do in other cases, and I'm already over the time, so I gotta run here, but so this is useful for traversing all kinds of trees, and syntax trees are what you get the most in Julia, probably. So some helpful links. I'm going to leave these for you to check out in the GitHub page, and that is it.